Atomic structure questions appear consistently in competitive exams because they form the foundation for all chemical logic. Success here depends on precisely identifying the relationship between subatomic particles and their respective charges. Before we understood the true architecture of the atom, J.J. Thomson proposed a model similar to a watermelon. He suggested the atom was a solid sphere of positive charge, like the red fruit, with negatively charged electrons embedded throughout like seeds. Ernest Rutherford tested this concept by firing high-energy alpha particles at a thin gold foil. If the atom were a solid mass, the particles would pass through with only minor deflections. Instead, while most passed straight through, a tiny fraction bounced almost entirely backward. This revealed a staggering difference in scale. The nucleus, with a radius of 10 to the power of -15 meters, is thousands of times smaller than the atom itself. If the nucleus is a cricket ball on a pitch, the atom's edge would be 5 kilometers away. This means the atom is almost entirely empty space. The concentration of mass in that tiny central volume is the core principle that governs all subsequent subatomic mass calculations. To calculate these particles accurately, we use two primary baseline formulas. Z represents the atomic number, which is the exact count of protons. A is the mass number, representing the total nucleons, the sum of protons and neutrons. It is important to note that the atomic number Z only equals the number of electrons when the species is perfectly neutral. When an atom gains an electron, it becomes a negatively charged anion. When it loses one, it becomes a positive cation. In both cases, the proton count remains the same, only the electron count changes. Let's apply this. Consider a species with 16 protons, 16 neutrons, and 18 electrons. Pause the video now to determine its chemical symbol and total charge. Here is the breakdown. 16 protons identify the element as sulfur. Because there are 18 negative electrons against 16 positive protons, we have a surplus of 2 electrons. This results in a -2 charge, or S2-. By treating the proton count as the fixed identity of the element and electrons as the variable, you can solve any ion calculation without confusion. Definitions for isotopes and isobars are often confused under pressure. We can use the structure of the words themselves to keep them distinct. In the word isotope, the letter P serves as a reminder of the identical proton count. These are atoms of the same element that differ only in their number of neutrons. For isobars, the syllable bar sounds like the word bar, or weight. These atoms have the same mass number, or weight, but different atomic numbers. A common misconception arises when comparing how these isotopes react. Because their masses are different, it is often assumed their chemical behavior must also change. In reality, chemical properties are determined by electrons, not mass. Since isotopes of an element have the same number of protons and electrons, they react identically. The difference in neutrons has almost no effect on chemical behavior. Finally, we have 3 key theoretical observations. Robert Millikan used this oil drop apparatus to prove that charge is quantized, meaning any charge Q is an integral multiple of E. For rays, gamma has the highest penetrating power, followed by beta and then alpha, and the radius of an atom is approximately 10 to the power of -10 meters. Internalizing these specific definitions and physical constants ensures you can answer theoretical questions quickly and with high confidence. We will integrate these concepts by solving 3 scenarios frequently appearing in advanced chemistry assessments. First, the ratio of the atom's radius to its nucleus. By dividing 10 to the power of -10 by 10 to the power of -15, we see the atom is 100,000 times larger than its center. Second, the instability of the Rutherford model. According to electromagnetic theory, an accelerating charged particle like an orbiting electron must lose energy. This would cause the electron to spiral into the nucleus in just 10 to the power of -8 seconds, which we know does not happen. Third, identifying the nucleons in an isotope like carbon-14. The superscript is the mass number, which by definition is the total number of nucleons. The answer is simply 14. We have moved from the early models to the specific math of ions and isotopes. Save this summary of formulas and definitions to use during your final review of atomic structure.
Thank you so much for watching. Subscribe our channel and stay updated for more lectures.